Hey everyone, today we're going to explore section 2.4. The main things out of 2.4 that you need to get are what's called the library of functions and piecewise defined functions. The library of functions is a set of the basic parent functions that most functions represent. So these are shapes that you should know, and I'm also going to link a couple of videos in e-learning so that you can practice them. But these are shapes that when I say f of x is equal to x squared, I want you to already have a picture in your head. For those of you going forward to calculus, this will make your calculus journey so much easier if you get these basic shapes down. So let's talk about the basic shapes. The first one is called the constant function, and that's f of x is equal to c, where c is some constant. So this would be like f of x is equal to, say, 1.3 or 4/3. So it is just a horizontal line and goes straight across the page. Now, if we are talking about domain and range when we're talking about these functions, this has a domain of all real numbers. So it goes from negative infinity to infinity. The range is only that one value of y. So it only gets the value of c, and it is that point c. For this one, it would be that 4/3. The next function in our library of parent functions is what's called the identity function, and this is the parent function for all lines. So all linear functions are some transformation based on this one identity function. There are changes in the slope and there are changes in the intercept point. But the original function, f of x is equal to x, is the straight diagonal line that goes through points 1, 1, 2, 2, 3, 3, and so on and so forth. Domain and range wise, both negative infinity to infinity on the identity function. Also goes through the origin. The absolute value function is a function that looks like the identity line in the first quadrant in the positive axis, and is a mirror image or reflection over the y-axis in the second quadrant. So this function here, the domain is all values of x, so it goes from negative infinity to infinity. The range does not have any negative values for y, so it starts at 0, including 0, goes to infinity here. People think of this like a v, so if you're thinking of the absolute value function, always looks like a v. Also goes through the origin. The square root function starts at the origin at 0, 0, and opens like a bird wing. So the square root function looks like this bird wing shape. This function domain, remember we cannot have a negative value inside a square root, so starts at 0, goes to infinity. Range, same thing. Starts at 0, goes to infinity. A related function is the square function or the quadratic function. Quadratic function has a vertex at 0, 0. Opens like a U on both sides of the origin. So this goes through the point 1, 1, goes through the point 2, 4, because each value of x that we put in, we square it to get the value of y. Our domain is all real numbers, so negative infinity to infinity. Range starts at 0 because everything is squared, goes to infinity. Now, cubic functions are also a power function. So you're putting in a value of x and raising it to a power. Goes through the origin. Looks kind of like an S-curve a little bit. So here, the cubic function, x cubed, has a domain of all real numbers. Now, since we can take a cube root of a negative number, or we can cube a negative number and keep its sign, our range is also from negative infinity to infinity. Now I'm going to add a related function to the cubic function, and that is the cubed root function. So if you have the cubed root function, f of x is equal to the cubed root of x, this function goes through the origin, so it has a point at 0, 0. And if you look at the square function and its relationship in shape to the square root function, these two functions here, you notice that the square root function is like the square function, just kind of tipped over and only the top side. The cubic function and the cubed root function are kind of similar in shape, where one is tipped over and the other. So the cubed root function comes in from the bottom, is shaped kind of like a cubic, just laying on its side. So here is the cubed root function. Domain and range, both negative infinity to infinity. The last one that we're going to cover is the reciprocal function, which is the function 1 over x. Now, the function 1 over x is the parent function to all of our rational functions. You notice that it has an x on the bottom, so it cannot include 0. So when we're talking about our domain, all values except for 0. Range, same thing, not including 0. When we get to rational functions, we'll discuss asymptote lines. It does have some asymptotes in there as well. Now, the other piece I wanted to talk about is piecewise functions. So piecewise functions are functions that follow different descriptions over parts of their domain. So for part of the domain, the function will do one thing and then it'll switch, and that at a different part of the domain it could do something else. So if I'm looking at a piecewise defined function, generally you have a bracket like this, and it shows the sections of the domain that each of the function descriptions is used for. So for values less than or equal to -1 in this case, we would plug x values into 2 minus 4x. If we have values greater than -1, we'd plug them into x squared plus 3. So if I'm looking for f of -3, -3 is less than or equal to -1. So I'm going to plug it into this top function. Simplifying the arithmetic, -4 times -3 gives me -12, so 2 plus 12 gives me 14. Using -1, -1 is the change point here, so I have to be careful of the inequality. So this first one is less than or equal to -1. So that's the one I actually plug -1 into. So 2 minus 4 times -1 gives me 2 plus 4, or 6. And f of 0, 0 is greater than -1, so now I'm using the bottom function. So I have 0 squared plus 3 equals 3. Now, if I wanted to graph a piecewise defined function, the first thing I need to do is see where it's changing its function description. Now, I'm going to make an alteration of this function just so it fits the graph better. So you have 2x squared plus 3. I want you to cross through this 2, and we're going to just graph x squared plus 3 for this section. So looking at this function, I have negative x plus 1 for x values less than negative 3. So negative 3 is right here. So this is the line where my function is changing from one function notation to another. So one description to another. I'm just drawing a yellow line here, not because it's part of the graph, but to remind me that I need to make a change there. So looking at this first graph, values less than negative 3. So I'm over here on this side. So looking at, say, 1, 2, and 3, function number 1 is going to be over here on this side. Now function number 2 is at negative 3. So that's right on the line. And it says the function is negative 2 at negative 3. So when x is negative 3, y is negative 2. We have just a simple point here. So negative 3, negative 2, and here's a point on that function. Now function number 3, x squared plus 3, that's going to be over here on the right-hand side of that yellow line. So I'm going to have 3 separate pieces of this function, which is why it's called a piecewise function. Now I'm going to graph each section. So this f of x, negative x plus 1, that's a line with a negative slope at an intercept point of 1. Now, my y-intercept is not in the region that falls in that function. So really I'm going to plot some points. So if we are at negative 3, we can start that line, but we have to use an open circle. So let's say we put negative 3 in there. I have f of negative 3 open circle at negative 3 plus 1. So positive 3 plus 1 gives me 4, and that line has an open circle here. Now I can plug some more points, or I can count it based on slope. So let's plug in negative 5. Negative 5 plus 1 gives me positive 6. So I have a point here, and then I'm just going to pen this in. It's this whole region on this side, so that's part of that piecewise function. Now at negative 3, I have that point. That is function number 2. Then function number 3 is x squared plus 3. So again, I'm going to try an open circle using that other one. Negative 3 squared plus 3. 9 plus 3 gives me 12. I'm still a little high off the graph, but we'll put it here. So here is my point at 12. Now I need a couple more points for that last one. So let's try f of negative 1. Negative 1 squared plus 3 gives me 4. Notice it's x squared plus 3, so we're expecting it to look like a parabola. F of 0, 0 squared plus 3 gives me 3. And if I go on the other side, this negative 1, plugging it in, gives me positive 1. Also true for positive 1. So I can get a basic idea of what this parabola looks like on that side there. So if you're graphing a piecewise function, figure out where your pieces are, use a line to mark the difference, and then you're just graphing a section of it. Plot as many points as you need to get a good graph, and then connect them together. Be aware of the open and closed circles. Let me know if you have any questions or concerns. I'm happy to help work through and practice that library of parent functions. Have a good day.